All right, let's explain that video.
Hi, everyone. So what is the story of this number? The principal square root of 3. I might just call it root 3 from now on. Principal square root of 3 is, in fact, a number. It equals 1.73 yada, yada, yada. It goes on and on and on without a repeating pattern. So the square root of 3 is an irrational number. It neither terminates nor does it have a repeating pattern like 1/3 does, 0.333 and so forth, 0.3 bar. So in that sense, root 3 is kind of like pi. Students often remember that root 3 is about 1.73. Root 3 is about 1.73 as an approximation. And what characteristics does this number have? Well, by definition, the principal square root of 3 has to satisfy this property. It is the unique non-negative real number that does the following. When you square it, you get the radicand, 3. Root 3 is the only number that satisfies those properties. It's non-negative, we want the principal square root, and its square is 3. Notice that even though root 3 is itself an irrational number and not an integer, it does turn out that 3 itself is an integer. So when you square something like the square root of 3 or the square root of 5, you end up with an integer, the radicand. Well, what is the square of the square root of 3? Well, it's the square root of 3 times itself. When you square something, you multiply something by itself. Now, it turns out that based on the rules of radicals, root 3 times root 3 is root 9. If the radicands are non-negative, here they are, they're both 3s, then the product of roots is the root of the product. The product of the roots equals the root of the product. We have square roots here, we have a square root here. 3 times 3, when you multiply the radicands, you get 9. And what is the principal square root of 9? Well, it is 3. It's the only non-negative property, it's the only non-negative number with a property that when you square it, you get 9. So look at this. The square root of 3 times itself is equal to 3. We often use this fact when we're doing things like rationalizing denominators. So that's why root 3, when multiplied by itself, gives us a really nice number, 3, a magical integer.
All right, so now I'm going to,
Hi, everyone.
let's go over the schedule now. All right, this is the last page of your syllabus. All right, so today is Thursday, August 20th, day 2. We're going to finish 0.5 on laws of exponents and radicals and applying them to simplify expressions. We're going to do 0.6 on classifying expressions in X, kind of like the numbers. And we're going to do most of 0.7 on factoring, although I don't think we'll finish today. We'll see what happens. I might have to do a live video today and kind of post that separately later. All right, and then your homework on chapter 0 is due Friday, September 4th, the day after the major homework session. Any questions? Any questions? See anything in chat? Okay, any questions? All right. So let's go ahead and start 0.5. Let's redo. Let's continue with 0.5. We reviewed radicals last time. That was what the root 3 thing helped out on. Let's now do laws of radicals, first laws of exponents, then laws of radicals. All right. Okay, now, gotta go to my, there we go.
Hi everyone, let's talk about section 0.5 on exponents and radicals. And let's go over these various laws for exponents and radicals. Now, you won't have to write out a sheet of paper and list out all these laws from memory. It's more a matter of know them when you see them. If you see the left side, be able to write down the right side and vice versa. Know what's equivalent, know what works, and also know what doesn't necessarily work. So let's take a look at some laws. All right. First of all, what happens when you multiply powers of x? What is x to the second times x to the third? Or x squared times x cubed? Well, what is x squared? If you were to ask an algebra student, what is x squared? What might the algebra student say? That x squared is x times x. Now, if you ask the algebra student, well, what's x cubed? Or x to the third? The algebra student may say, well, that's x times x times x. So then when you multiply all these together, you get x to the what? 1, 2, 3, 4, 5. You get x to the fifth, not x to the sixth. It's a common mistake. You get x to the sixth. Sorry, x to the fifth. Almost made that mistake. X to the fifth. When you multiply powers of x, you add the exponents. 2 plus 3 is 5. You don't multiply them. And that takes us to law number 1. We're assuming these are all real valued. To multiply powers of x, you add the exponents. For example, x to the second times x to the third is x to the fifth. In general, x to the m times x to the n is x to the m plus n. And what happens when you divide powers of x? Well, let's take this original statement over here, right? And let's start by turning it around. Okay, so I'm going to put the x, I'm going to put the x to the fifth on the left. I'm going to put the x squared times x to the third over on the right. You can always switch around a minus sign. So x to the fifth equals x to the second
Equal
times
sign.
x to the third. Now, I should copy this down in the next step, but let's make this fast. All right, let's divide both sides by x to the third. Let's divide both sides by x to the third. Don't write a big fraction bar, by the way. You should never put a fraction bar under an equal sign. All right. So now, what is x to the fifth divided by x to the third? Well, what happens on the right side? X to the third divided by x to the third. Well, that is just going to be 1. Technically, we should put a 1 up here and a 1 down here. We want to indicate what's left. Okay, all right? So we have x squared times 1 divided by 1. Bottom line is we have x squared. So x to the fifth over x to the third equals x to the second. Again, I should write this as a separate step. But look at this. When you divide powers of x, what do? It looks like you subtract the exponents. 5 minus 3 is 2. There's another way of looking at this. Okay, what is x to the fifth? What is x to the fifth? It's x times x times x times x times x. Fraction bar. What's x to the third? Down here. That's going to be x times x times x. What happens when you have 5x's over 3x's? and we're multiplying up here and down here. Well, we get a bunch of cancellations. So x divided by x is 1. I'll just put ones here. X divided by x is 1. X divided by x is 1. X times x is x squared. In general, to divide powers of x, you subtract the exponents. X to the m over x to the n equals x to the m minus n.
Okay, any questions
Hi,
so
everyone.
far? Any questions so far? These videos are short because I was afraid of making a mistake. Okay. All right, what happened to the captions here? They'll be captioned on the Zoom, but they'll be captioned on the when I load this up. That's strange. Huh. Well, let me quickly check this. English, yeah, it just didn't caption. Huh. That's strange. All right. Oh, well, let me let's do this again.
Hi, everyone. Back to sets.
Whoops. Sorry. All right, let me fix this. That does Tuesdays. Here's Thursdays. Thursdays part 3. Here we go.
Hi, everyone. So we just talked about how x to the 5th divided by x to the 3rd is x to the 2nd, not 5/3, second. We subtract the exponents. Now, these two expressions are equivalent, except when x is what value? When x is what real number? When x is 0. We never divide by 0. And if you try to divide by x to the 3rd, you're trying to divide by 0. So there is what I call a hidden restriction here. That's not an official term, but I'm going to refer to this a lot. And this comes up a lot when we talk about issues of domain later on in chapter 1. So x to the 5th divided by x to the 3rd, we can do that as long as x takes on any non-zero real value. Then the result is x squared. But in order for these two expressions to be fully equivalent, we should really tie these two things together. X to the 5th divided by x to the 3rd, you should really rewrite that as x squared, but remind us x cannot be 0, because it is not evident from this expression, x squared, that 0 is an illegal value for x. So that's when a restriction is hidden. If it's not clear that restriction applies here. If you look at x squared, it looks all good. It looks like it's good for all real values of x. But because x cannot be 0 back here, we cannot divide by 0. 0 is also illegal for x over here, in order for these two expressions to be truly equivalent. Hidden restrictions, that's going to come out once in a while, especially in chapter 1, when we talk about domain. You should write these down. Granted, in trig, we're often going to forget about them.
All right. Any questions? Any questions? Sometimes I can address a few like homework points in the chat, but going over homework problems fully, we can do that after class more comprehensively. Any questions? Any questions? Okay, going on.
Hi, everyone. Let's do the next 3 laws. All right. How do we raise a power to a power? What if we have x to the 2nd all to the 3rd, all raised to the 3rd power? We're raising a power to a power or exponent. Sometimes the word power is interchangeable with exponent. Sometimes a power means like x to the 2nd. All right. Well, what is the cube of anything? When you cube anything, what do? You take 3 copies of the thing and multiply them together. So the cube of x squared is x squared times x squared times x squared, right? Well, that's going to be x to the, remember, when you multiply powers of x, what do you do to the exponents? You add them. You add them. But now, what is 2 plus 2 plus 2? 2 plus 2 plus 2, you can think of that as 3 times 2, or 2 times 3. 2 times 3 is 6. 2 plus 2 plus 2, or 2 times 3, that's 6. So now we have x to the 6th. When you raise a power to a power or exponent, you multiply the exponents. Here we get x to the 6th. To raise a power to a power, you multiply the exponents. Now, what if you take the power of a product? What if we have the square of x times y? Well, when you square a product, you take the product of the squares. When you raise a product to a power or exponent, you share the exponent. The square of xy ends up being x squared y squared. Why is that? Well, what's the square of anything? You take that thing and multiply it by itself. We have xy times xy. Now, because multiplication is associative, it doesn't matter how we group these things, xy, xy. Multiplication is also commutative, meaning that we can switch the y and the x, order doesn't matter, and we get x, x, y, y. So then, what do we end up with? Well, as promised, we get x to the 2nd times y to the 2nd. X squared, y squared. When you square a product, you square each factor. The power of a product equals the product of the powers. In other words, you share the exponent among the factors. This does not work with addition, however. All right. The power of a product is the product of the powers. You share the exponent. For the power of a quotient is a similar idea. We have the square of x over y. When you square anything, you get the thing times itself, x over y times x over y. We then multiply across. On top, x times x is x squared. And on the bottom, y times y is y squared. So kind of like with a product, when you raise a quotient to a power, you share the exponent. When you raise a fraction to an exponent, each part gets the exponent, x squared over y squared. The power of a quotient equals the quotient of powers. You share the exponent. Now you might be wondering, well, wait a minute. This is illegal if y is what number in value? Well, y cannot be 0, right? But that should be evident from this final expression, right? It should be evident here that y cannot be 0. So there is a restriction, but it's not hidden. So we don't have to write that y cannot be 0. Although if you want to, that's fine. Once again, the power of a quotient is the quotient of the powers. This over here. You share the exponent. Now again, you do not share the exponent if you're dealing with addition or subtraction. That does not work. The square of x plus y is not x squared plus y squared, but it does work for multiplication and division. Next up, we're going to look at 3 laws that may not be as obvious to you.
Okay, now, before I go on, I wanted to get into this division by 0 issue. Remember, you never divide by 0. And here's a funny little video to help express that. Any questions, by the way? Any questions? Okay, let's proceed.
Hi, everyone. Let's take a look at these last 3 laws for exponents. First of all, x to the 0 equals 1, as long as x is not 0. Bear in mind, 0 to the 0 is sometimes defined to be 1 if you're dealing with polynomials. All right, let's talk about that. What is x to the 2nd divided by x to the 2nd? Well, first, let's use the laws of exponents. If you divide powers of x, what do you do to the exponents? You subtract them. 2 minus 2 is 0. But now, wait a minute. What's another way of looking at x squared divided by itself? Well, anything divided by itself, almost, anything divided by itself is going to be what? What's 9 divided by 9? It's 1. So x squared divided by x squared is also equal to 1. So then it makes sense that x to the 0 is equivalent to 1. X to the 0 is equal to 1. But wait a minute. Something divided by itself is 1 as long as that something is not what number? What value? 0. We cannot say this if x is 0. So technically, there's a hidden restriction here. X squared divided by x squared, or x to the 0, is equal to 1. It's equivalent to 1 if x is not 0 in value. Otherwise, this here is undefined. Now, 0 to the 0, you might call that undefined. Again, sometimes it's called 1 in polynomial theory, but we'll talk about 0 to the 0 later. But if x is not 0, certainly x to the 0 is 1. What's 2 to the 0? I'll go over here. What's 2 to the 0? 2 to the 0 is going to be 1. This over here. 2 to the 0 equals 1. What's 3 to the 0? Also 1. What's your social security number to the 0? It's 1. What is that again? All right. X to the 0 is 1. Now, this over here, 1 over x to the n equals x to the opposite of n. Basically, the x to the n, the power of x, can move over here if you flip the sign on the exponent, if you take the opposite of the exponent. Let's discuss that. Let's look at 1 over x squared. Now, again, 1 is x to what exponent? We're assuming x is not 0 in value. 1 is x to what exponent? 0. When you divide powers of x, what do you do with the exponents? You subtract them. 0 minus 2 is negative 2. So 1 over x squared is equivalent to x to the negative 2. In general, 1 over x to the n equals x to the opposite of n. You flip the sign on the exponent if you want the straight power of x. Now, one way to look at this, remember that a fraction has 2 parts. A numerator and a denominator, a top and a bottom. 1 is the numerator or top, x squared. Okay, 1 is the numerator or top, x squared is the bottom or the denominator. Now, if you have a factor of 1 part, you can flip the fraction in such a way that a factor on 1 part can become a factor on the other part if you change the sign of the exponent. Now, bear in mind, if you have a 2 up here, you don't get a 2 down here. But for ones, this does work out. So if you divide x to the second on the top, you get that. If you divide x to the second on the bottom, you get that. So again, you can think of the x squared here as a factor, a part of the denominator. It is the denominator. A factor of a part of a fraction can flip to the other part of the fraction if you change the sign on the exponent. It also works backwards. If you have x to the negative 2 up on top, you can move that as a factor on the bottom, in fact, as the bottom, as x to the positive 2, flipping the sign on the exponent. So it also works backwards. Let's assume that x is not 0 here. But that's not hidden. All right, how about this? 1 over x to the negative 2. We have a part, a factor of the bottom. In fact, that is the entire denominator. This factor of the bottom can flip over as a factor on the top by changing the sign of the exponent. So x to the negative 2 down here becomes x to the positive 2 up here. And again, when you multiply by x squared on the top, you get x squared. If you multiply the bottom by x squared, you get 1. Bear in mind, we're not flipping the entire fraction. Okay, so if this were a 2, we don't get a 2 down here. The flipping does work if you have a 1 in the other part. All right. Now, for number 8, I'll go straight to my explanation over here, my note. What is x over y all to the negative 1? Remember, over here, x to the negative 1 is 1 over x, right? If you forgot that, x to the negative 1 is 1 over x. We're applying this rule over here, right? X to the negative 1 is 1 over x. So x over y all to the negative 1 is 1 over this base, x over y. Now look over here. X to the negative 1 is 1 over x. When you raise something to the negative 1 exponent, you're taking the, what's that, R word? You're taking the reciprocal of the base. You're taking the reciprocal of the base. So likewise here, if you raise x over y, that base, all to the negative 1, you're taking the reciprocal of that base. You get 1 over x over y. And what is the reciprocal of x over y? It's y over x. If you don't see that, we can do this. Here's 1 over x over y. Multiply top and bottom by y over y. We're assuming that y is not 0. That does turn out to be our hidden restriction, by the way. Y is not 0. Y cannot be 0. All right, so 1 over x over y, all right? We multiply top and bottom by y. You're multiplying by 1. We're assuming y is not 0, so we are, in fact, multiplying by 1 here, all right? 1 times y is y, up on top. Down here, x over y times y. These cancel each other out. I should put little 1s here. And we get x over here. The reciprocal of x over y, when you multiply by 1 in the form of y over y, okay, you get y over x, the reciprocal. Likewise, over here, the reciprocal of x over y is y over x. Now, you might be going, hey, wait a minute. I know x cannot be 0. How come we don't write that? You can if you want. That's not a hidden restriction. That is what I would call, I'm using my own terminology here, but I would call x not being 0, that's an evident restriction. It's not hidden. It's in plain sight, basically. It's in plain sight, x cannot be 0. If you want to write that down, that's fine. That's totally correct. But you don't have to because it's evident from the expression, x cannot be 0. In a way, what's more key is the hidden restriction. When you look at y over x, it's not obvious that y cannot be 0, unless you look at the beginning. Hey, wait, I'm trying to divide by 0 here. Y cannot be 0. So remember, if you're ever dividing by 0, if you have a value for y that ever makes you divide by 0, then y cannot be 0, even though it looks legal here for y to be 0. If 0 is illegal over here, 0 is illegal over here, it's not evident, you should write that hidden restriction. So again, this whole deal with hidden restrictions, that'll come up when we're talking about domain. This over here, that's a hidden restriction. You should write down hidden restrictions. If you want to write down the evident ones, that's fine. You don't have to. Next, we're going to talk about the laws of radicals that are related to these laws of exponents, because you can always write a radical in terms of powers with exponents. Next time.
Okay, any questions? Because I went over this because before in class, when we were on campus, seems ages ago, I had to go over this because people got really stuck around here. Any questions? Any questions? A lot of people got stuck around here. Okay, and after class, I may need to go back to this. Any questions? Any questions? By the way, I'm going to elaborate on number 8 in just a moment. Well, yeah, I'm going to elaborate. It may help if I elaborate. So let's start video 6. Let's elaborate. Because I realized I forgot to do the general law 8. Okay, so let's do that. Let's see if this helps.
Hi, everyone. I'd like to generalize this over here to the general statement in number 8 over here. So before, I talked about how the reciprocal of x over y all raised to the -1 exponent, is y over x. That's called the reciprocal of the base, x over y, with y not being 0 as a hidden restriction. Well, let's look at a more difficult example, x over y all to the -2. Well, similarly, this can be rewritten as y over x all to the +2, where again, y not being 0 is a hidden restriction. You cannot divide by 0 to the left here. On the left side, you're not allowed to use y equals 0 on the right side either. Now remember, as you move from the left side to the right side, the goal is to get an equivalent expression, such that as long as these represent real values, they are equal to each other. In particular, all cases where x and y are not equal to 0. Now, to get from the left side to the right side, what can you do? We don't like these negative exponents. We can take the opposite of that exponent, that is, we flip the sign on the exponent, here from negative to positive. We can do that provided that we take the what of the base. If we take the reciprocal of the base. The reciprocal of x over y is y over x. So again, to get an equivalent expression, because we don't like these negative exponents, you can take the opposite of the exponent, that is, flip the sign, so that the result here is positive. And if you flip the sign on the exponent, you also need to take the reciprocal of the base. In general, x over y all to the opposite of n is equivalent to y over x all to the n. To flip the sign on the exponent, to take opposites on the exponent, you also have to take the reciprocal of the base. So that's number 8 in its full glory for laws of exponents. Now let's go to laws of radicals.
All right. So again, those are some gymnastics that confuse people. And I had a question in chat about that. Any questions there? I mean, remember, I do have these boards I can write on. Where are they? Okay, I do have boards I can write on if you need that. Yeah, all these. All right. Any questions? Any questions? All right, let's go to laws of radicals. Any questions? I asked questions in there too.
Hi, everyone.
Wait. Let me get a question here. All right, question here. Why is y cannot equal 0 if y is in the... Oh, I mean in the final expression. Okay, if I go back. Oh, wait. Okay, wait. Okay, let me do this then. Okay, over here. So I call it a hidden restriction because I'm focusing on y over x. So if I ask you, what's the reciprocal of x over y? If you say y over x, see, I can't tell that 0 is illegal for y because I look at y over x and I go, well, hey, if you put 0 on top, there's nothing illegal about that. But the thing is, you're right. 0 is illegal for y if you look over here. But if I hand this over to the teacher, okay, it's like, that's my answer. Okay, well, how do I know that y cannot be 0? You have to state that. And that reflects the fact that y was in the original expression. All right? Okay. Yeah, all right. Any other questions? Again, feel free to chat. Although remember, I'm showing the video, so I can pause though. If you want me to pause, I can pause. All right.
In section 0.5, let's now talk about laws of radicals, which are related to the laws of exponents because you can always rewrite a radical as a power with an exponent. Now, we're going to assume here that we're dealing with real valued expressions. So for example, if we consider the cube root of -1, that's fine because the principal cube root of -1 is -1. The cube of -1 is -1. That's fine. -1 is a real value. However, -1 does not have real square roots. The principal square root of -1 we call I, but that's not real. That doesn't count. So we're not allowing things like the square root of -1, or for that matter, the 4th root, the 6th root, the 8th root, any even root of a negative value. We're not allowing those now. For now, we're keeping it real. So the square root of -1, no good. Cube root of -1, odd root of a negative value, that's still fine. All right. Law number 9. The square root of xy equals the square root of x times the square root of y. Or, one way to look at this, it's easier to read it in reverse. So, for example, the square root of 2 times the square root of 3 does equal the square root of 6. That does work out. If you don't believe me, square both sides and see what happens. So the product of roots does equal the root of the product. Of course, we're dealing with the same roots here, square roots. Although this also works with cube roots or 4th roots. The product of roots equals the root of the product. So going in reverse, the square root of x times the square root of y equals the square root of x times y. That does work. And it works this way as well. Likewise, if we divide both sides by the square root of 3, let's say, well, these cancel out. Root 3 divided by root 3 is 1. And we get that. Root 6 divided by root 3, the right-hand side here, equals the left-hand side. Root 2. Root 6 divided by root 3 is root 2. When you divide roots, you divide the radicands. The quotient of the roots equals the root of the quotient. The quotient of the roots equals the root of the quotient. This works out cleanly. Root x over root y equals root x over y. Another way to look at it, the radical breaks up, both for the square root of a product or a quotient. The square root of a product breaks up like so. The square root of a quotient breaks up like so. You share the radical. So if you're taking the radical of a product or a quotient, you can share the radical across the factors or across the top and the bottom. However, this does not apply to the radical of a sum or a difference. So in general, the square root of x plus y is not in general equivalent to the square root of x plus the square root of y. The radical does not break up over sums or differences in general. Right? So don't be deluded into thinking that. For example, consider the square root of, let's consider a counterexample to the conjecture that this is true. Right? Let's say a student naively thought that this was true. Right? Then you're claiming that the square root of 1 plus 4 is equal to the square root of 1 plus the square root of 4. On the left side, we have the square root of 5. The square root of 1, the principal square root of 1 is 1, plus the principal square root of 4 is 2. Well, folks, is the principal square root of 5 equal to 3? Is the square of 3 5? Is 3 the square root of 5? No. No good. That's really no good. No good. Our conjecture here is false. It's not a theorem. Because we found a counterexample where x equals 1, y equals 4. The conjecture failed. The conjecture was false. So, radicals break up over products and quotients, but not over sums or differences for that matter. Be careful. It's often the case that we can do things with products and quotients, but not sums or differences. That's also true for exponents. Number 11, we're not going to worry so much about. An example of this is the cube root of the square root of x is the sixth root of x. Ultimately, you can get this from the laws of exponents and relating exponents and radicals, but don't worry so much about number 11. Next up, we're going to talk about how to unravel radicals using powers or exponents. That's next time.
Any questions? Any questions? Doing the rules for radicals here. Any questions? So it's a matter of what you can do and cannot do. And seriously, a big skill that you need to get out of this pre-calculus class. What are the things you can do and what are the things you cannot do, right? So you might be able to do some things with products and quotients, but maybe you cannot do those things with sums or differences, like with radicals or exponents, or sine or log. Sine and cosine got problems anyway, but log, yeah, we also have a distinction. Questions? Questions? All right, moving on to these other laws.
Hi, everyone. Let's continue with laws of radicals. So for example, if you had the square of the square root of x, how could you simplify that? Well, the square and the square root undo each other, and this does simplify to x, provided that x is not what? We only take the square roots of what kinds of values or numbers? Non-negative. Non-negative. Remember, if we have the square root of -1 in there.
Sorry, my feet is kind of freaking out. Hold on a second.
Hi, everyone. Let's continue with laws of radicals. So for example, if you had the square of the square root of x, how could you simplify that? Well, the square and the square root undo each other, and this does simplify to x, provided that x is not what? We only take the square roots of what kinds of values or numbers? Non-negative. Non-negative. Remember, if we have the square root of -1 in there, we're dead right there. Okay, don't mess with that. Don't go there. Right. So the square of the square root of x is x. That does work out, provided that x is non-negative. All right. Now, what about the cube of the cube root of x? Well, the cube and the cube root undo each other. We get x. Now, we do not take the square root of a negative number because that's not real, but can we take the cube root of a negative number? What's the cube root of -1? The principal cube root. It is -1. So this works out. And it turns out that this statement is in fact true. We're going to use this notation now. It's true for all values of x in the reals. So see this set notation? This is true for all values of x in the reals. This is true for all real x, even the negative values of x. All right. So what is number 12? Law number 12. The square of the square root of x is x. The fourth power of the fourth root of x is x, and so forth, if x is non-negative. That's a condition. Otherwise, we have a problem of non-real quantities in there. But if you have something like the cube of the cube root of x, like this, or the fifth power of the fifth root of x, that's x for all real values of x. So you see, there are differences between even roots and odd roots. And actually, you like odd roots better. I know I'm telling you how to think, but you like odd roots better because you don't have these special deals here. Now for law 13, let's consider this. What if we go the other way around? What if we put the power on the inside, the root on the outside? What is the square root of x squared? Now, if you know me by now, you might be thinking, is it x? Well, again, that's true if x is non-negative. But then you might argue, well, wait, if x is negative, the square takes care of that sign issue, right? Okay, the square of a real value is never negative. That's true, but let's do an example here. What if x is a negative value? Okay. So if x is, for example, -3. This all works very cleanly if x is +3, check it out. But what if x is -3? Let's see what happens here. All right, the square root of the square of -3. The square root of the square of -3. Please put, I'll put this in a dark red here. Please put grouping symbols around here. Okay. Whenever you substitute or plug in, be prepared to put grouping symbols. Okay, the x is replaced by, in this case, parentheses, -3. What is the square of -3? The square of -3 is +9, right? It's important you put the grouping symbols there because, and a lot of engineers mess this up. What's this? As it stands, what's this based on the order of operations? You could read this as -1 times 3 squared. But which comes first? Multiplication or exponentiation? The exponentiation comes first. It's -1 times 9. We get, in the end, -9. I get scared when I hear that engineers don't know that, okay? As this stands, the opposite of 3 squared, that's -9. With grouping symbols here, we end up with +9. Now, what's the principal square root of +9? That is going to be +3. But wait a minute, we start off with -3 inside here. 3 is not equal to -3. 3 is the what of -3? Well, it's the opposite of -3, but it's also the what of -3. 3 is the what of -3? It's the absolute value. So here's the rule for number 13. Again, the even roots are harder. Okay, the square root of x squared is not x in general. It's true for non-negative values of x, but in general, the square root of x squared is the absolute value of x. If you want this to be true for all real values of x, in general, this here is the absolute value of x. To make sure this is correct for negative values of x as well. So in general, the square root of x squared is the absolute value of x. If you want this to be valid for even the negative values of x. Although, if you consider the other way, well, if you consider odd roots, right? The odd root of the corresponding power. The cube root of the cube of x, that's straight up x. The fifth root of the fifth power of x, that's straight up x. In fact, it's wrong to put absolute value. For example, if x is -1 in here, you end up with -1 out here. It would be wrong to put absolute value. So again, the odd root case is easier. Okay, the odd root case is easier. That makes us happy. You like odd roots. You don't like the even roots so much because you have a condition as number 12, or in this case here, you need to put absolute value. In the bottom here, I have some warnings, all right? By the way, the rules for the root of a product, that's related to the idea of simplifying radicals, right? Root 18 is root 9 times root 2, and that's 3 root 2. So basically, the 9 factor in the 18 pops out as a 3. So that's the idea of simplifying radicals. And I do a review of some fallacies. Do not think that this is equivalent to that. Same for differences. And remember, we're keeping things real. Don't mess with things like that for now. Okay. And again, you like odd roots. Even roots, they can mess you up sometimes. You might need conditions, such as the non-negativity condition, or you might need absolute value. Next up, we're going to express expressions in different forms. Radical form, exponential or power form, fractional form. Next time.
Actually, before you go to that, it's a nice time for a little segue, little video, because I'm telling you how to think, right? You like odd roots and odd powers because they work out cleanly. You don't like even roots and even powers so much. And when I tell students that, I'm often reminded of this clip from The Simpsons. Whoa, wait a minute. Careful. Gotta pause. YouTube's okay with a little bit, but okay. I'm telling you folks, you like odd roots, like cube roots and fifth roots, and their corresponding powers. You're not going to like square roots and fourth roots as much because you got to worry about the whole negative number thing, right? Watch out for those things, or absolute value. Okay, let's proceed.
Hi, everyone. We're going to talk about equivalent expressions involving fractions, radicals, and powers, or expressions with exponents. This is really key in calculus. You have to know this. It's your bread and butter. Because sometimes when you take derivatives and integrals of expressions or functions, it's important to rewrite them. So we're going to consider pairs of equivalent expressions together with relevant restrictions, including hidden restrictions. This is related to the important domain issue in section 1.1. Now, as far as domain or restriction issues go, what are the two things that you never ever do if you want to keep things real, if you want to keep it real? You never divide by what number? And you never take square roots, fourth roots, in general, even roots of what kinds of numbers or values. So, restriction issues. The restrictions guarantee that we never do the equivalent of dividing by 0, right? That includes doing things like this. If you see 0 to the negative 1, that's undefined. That's not real. That's no good either. So dividing by 0, that's a sin. Also, taking the even root of a negative value. Like if you take the square root of negative 1, that's a sin because that's not real. We need to keep it real. All right, I'm going to play some cover-up games here. Like a politician. All right, gotta be careful though. All right. And don't confuse exponential form with exponential functions. Really, I might use the term power form when I'm using exponents. All right, here we go. Let's see if this works. All right. 1 over x. How can you rewrite that as a power of x? And what are the restrictions? Domain restrictions. 1 over x. Remember the laws of exponents? That's going to be x to the negative 1. If you forgot your laws of exponents, I'll pull up the laws of exponents, all right? Over here, remember? X to the negative 1 is 1 over x. It was related to number 7. X to the negative 1 is 1 over x. All right. Oh, and x cannot be 0. You never divide by 0. That's the restriction. But it's not hidden. It's evident. How about 1 over x squared? That's going to be x to the what? That's going to be, again, by this rule 7 here, 1 over x to the second is x to the negative 2. Again, x cannot be 0, because then we'd be divided by 0. First two, not so bad. Oh yes, you're going to see guys like this in calculus. 1 over 7x to the negative 4/3. Write this as a constant times a power of x. A constant times a power of x. In fact, let's actually work it out. Let's work it out. All right. So we can split this up as 1/7 times 1 over x to the negative 4/3. So I'm breaking up that fraction into a product of two fractions. The coefficient is 1/7. Okay? So bear in mind, the 7 down here does not pop out as a 7, all right? If you have a 7 down there, the corresponding factor is 1/7, and that's the coefficient here, 1/7. See, the negative exponent here, it tricks people into thinking they can move up to 7. But the base for the negative 4/3 is x, not 7x. The negative exponent has nothing to do with the 7, right? So our coefficient here is 1/7, not 7. Okay, now the x to the negative 4/3, remember, we had a rule over here, all right? X to the negative 4/3, okay? We're basically using rule 7 again, except n is a negative number this time. We can do this sort of popping or hopping rule, all right? So x to the negative 4/3, it's in the denominator. Okay, it is the denominator. It's certainly a factor of the denominator. That can pop out or pop up in the other part as x to the positive 4/3. That's really messy. X to the positive 4/3. Right. So we can think of this as (1/7) times x to the positive 4/3, which you could then move up to the numerator if you like. Okay, 1 times that is that, so you can move this up to the numerator. All right, bottom line. And also consider restrictions. Is a restriction on x? Bottom line. I think it's going to be 1/7 x to the 4/3. Well, looky here, 1/7 x to the 4/3. And again, if you wish, you can rewrite this as a single fraction, x to the 4/3, all over 7. That's also acceptable. Now, because of the negative exponent on x, if you have x to any negative exponent, then x cannot be 0. There's no way that's going to work out. But then you might be wondering, well, would negative numbers work out? So you could consider 3 cases here. Let's consider 3 cases. The case where x is positive, the case where x is 0, and the case where x is negative. It's like an SAT test, right? So let's think about it. If x is a positive value, do things work out? Well, there's no reason things shouldn't.
Okay,
We have a cube root here.
my internet lagged. Let me go back a bit. My internet lagged a bit. Okay, let me go back.
X is 0.
Wait, before here, or I think I saw that note. Hold on. Okay, how far do I have to go? Any questions here? Okay, so go ahead and chat.
All over 7. That's also acceptable.
Okay, so is everyone okay up to there? Is everyone okay up to there? Okay, the main thing is that you get it. Okay?
Now, because of the negative exponent on x, if you have x to any negative exponent, then x cannot be 0. There's no way that's going to work out. But then you might be wondering, well, would negative numbers work out? So you could consider 3 cases here. Let's consider 3 cases. The case where x is positive, the case where x is 0, and the case where x is negative. It's like an SAT test, right? So let's think about it. If x is a positive value, do things work out? Well, there's no reason things shouldn't. We have a cube root here and a 4th power here. Okay, well, I guess I'll look over here, right? Okay, we have a cube root here and a 4th power here, right? And we basically have those ideas down here, right? Okay, so we don't have any problems with positive values of x. But what about x equals 0? We have a problem right here. If you have x to a negative exponent, you're dead right there. Can x be negative? Well, basically, we're looking at this cube root issue, and we can take the cube root of a negative number. So positive values of x are okay. Negative values of x are okay. However, 0, that's not good. So positive, negative values of x are okay, but x equals 0, that's no good.
I should put an X there. I should put an X there.
So we're relating here fractional forms with exponential or power forms. Here we wrote the expression, we rewrote it as a constant coefficient times the power of x. And there was a hidden restriction. It's not evident in this final expression that 0 is still illegal for x. So we should include this hidden restriction.
By the way, one comment. As you play the YouTube videos, you should quickly do this. Do exit full screen and enter full screen, because when you exit full screen, you can see my corrections. So sometimes I have corrections and I put them in the comments. So always check the comments to check for corrections. So exit full screen sometimes.
In restriction, x cannot be 0. Next up, we're going to talk about radical forms more explicitly.
Okay, so we'll do the next part. We'll take a break after the next part. Any questions right now? Any questions right now? Right. Some technical issues today. All right, so let's go on.
Hi, everyone. So let's now go back and forth between radical form and exponential or power form. And what are the corresponding domain restrictions? Real values of x that would work to keep things real. Okay, so the square root of x, the principal square root of x, is x to the what? And we only take the principal square root of what kinds of real values of x to keep things real. The square root of x is x to the 1/2, and we only take square roots of non-negative real values. So you have a little checklist here. If you have something involving x, right? Can x be positive? Yes. Can x be positive? Yes. The square root of 0 is 0. That works out. Can x be negative? No. We do not take square roots of negative values if we want to keep things real. All right. What about the cube root of x? The cube root of x. That's x to the what? And are there any restrictions? The cube root of x is x to the 1/3, but we can take cube roots of, well, positive values. We can take the cube root of 0, that's 0, and we can take the cube root of a negative number. The cube root of -1 is -1, for example. So we can take the cube root of any real value. There are no restrictions, assuming that x is real. We're assuming x is real. All right. Next up. Oh, and by the way, in case you forgot that, I'll refer you to my old notes. Refer you to my old notes over here. Remember, the square root of x is under right under part B. The square root of x is also written as x to the 1/2, the principal square root of x. And remember, the nth root of x is also written as x to the 1/n. So for example, the cube root of x is x to the 1/3. The fourth root of x is x to the 1/4. Don't confuse these with negative exponents. So remember, x to the 1/2 is the principal square root of x, but x to the -2 is what? X to the -2 is 1/x squared. A lot of people mix these up. Remember, fractions tend to correspond to radicals. Negative exponents tend to correspond to fractions. All right, moving on. This guy here. 3 times the 7th root of x to the 5th, or 3 times the 5th power of the 7th root of x. It turns out these are equivalent. Now, why am I putting parentheses, by the way? Not just to distinguish between these two expressions, although they are equivalent, but there's another reason. If I didn't have parentheses, what are you in danger of mistaking this for? I think a lot of students might be in danger of mistaking it for this. 3 to the 7th all times the square root of x to the 5th. If you saw something like this, right? Aside from the fact I have messy screenwriting, is this the 7th root or is it 3 to the 7th? Which is it? So when in doubt, if there's ambiguity, put grouping symbols, all right, to be safe. Trust me, in this pre-calculus class and later on, grouping symbols are really your friend. When in doubt, put grouping symbols. You have no idea how important they are and how often they'll save your skin. Anyway, back to the main point at hand. All right, so we have here 3 times what power of x? 3 times x to the, either way you cut it, it's going to be x to the 5/7. And think about any restrictions, right? So it is going to be 3 times x to the 5/7, whether you take the root before the power or, whether you take the power before the root or whether you take the root before the power. Either way, you're going to get 3 times x to the 5/7. Now, restrictions. Are there any restrictions? Let's look at possible cases here. Let me go to my my case sheet.
I remember I had to edit the video here because it took me a while to figure it out. There we go.
Hi everyone. Let's simplify.
Whoa, wait a
this
minute.
kind of
You know what?
logic.
I think I loaded up the truncated video. Let me get the good video. All right. Okay, so okay, so this is okay.
Hi everyone. So let's now go notes. Moving on. Whether you take the power before the root.
Okay, let me check this. Yeah, I had trouble with with this video here. Okay, let me check this. Part 2. Okay, let me play the part 2 then. This isn't I'll capture on Zoom. But,
So now, what is this? Writing 3 times what power of x? All right, we have the 3. That's just that coefficient out there. Times x to the what? Either way, it's going to be x to the 5/7. X to the 5/7. 5 indicating the power, 7 is the root index. 3x to the 5/7. Now, are there any restrictions? Well, let's look at these 3 cases. If x is positive, any trouble there? You might want to look at the radical form. Well, the 5th root of a positive number is positive. The 5th power of a positive number is positive, and the 7th root of a positive number is positive, real. So we're good there. How about 0? Well, power of 0 is 0, root of 0 is 0. That's fine. How about negative? The 5th power of a negative number is negative. The 7th root of a negative number, not a problem. It's a negative real number. It's all good, all reals, no restrictions on the domain. 3x to 5/7, no restrictions. Okay, next up, we're going to look at combinations, combined forms. 1 over the square root of x. 1 over the square root of x. So that's going to be what? X to what exponent in the end? Well, we have 1 over the square root of x is x to the 1/2. And then x to the 1/2 can come up or come out as x to the what? As x to the negative 1/2. So we have both a fraction and a negative sign in the exponent. And what are the restrictions? What are the restrictions? It might help to look at this combined form with the radical, All right, what are the restrictions? Okay, well, let's look at these three cases. Can x take on these various values of x? Can x be positive? Sure. Not a problem there. Can x be 0? Ah, the square root of 0 is 0. The problem is that we'd be divided by 0 in that case. So that, my friends, is no good. Can x be negative? The problem there is not so much the fraction, it's the fact that we have what kind of root? We have a square root. And we don't take square roots of negative numbers and keep things real. So that's no good either. X has to be positive in value. X has to be positive in value. All right. So we have x to the negative 1/2. X has to be positive in value. All right. Now, what about 1 over the cube root of x? How's that going to be similar and different? 1 over the cube root of x. That's going to be x to the what? And what restrictions are there? All right. So we're going to have here 1 over, well, the cube root of x is x to the 1/3. Again, that can pop out or up. If you're popping from, if you're hopping from bottom to top, you can also go from bottom to out. Bear in mind that if you have a negative exponent on top, then you have to be more careful, right? But x to 1/3 on the bottom basically goes up to x to negative 1/3 out or on top, right? So we have x to negative 1/3. And what are the restrictions? Okay, well, here are the various possible values of x, okay? Can x be positive? Not a problem. Can x be 0? Then you're going to be divided by 0 in the end. That's no good. Can x be negative? Actually, the cube root of a negative number is negative. That's okay. Move this up a bit, right? The cube root of a negative number is okay. 1 divided by a negative number, that's not a problem. That's a negative real number. That's actually okay. That's actually okay. So x cannot be 0. That's the only restriction. We have x to the negative 1/3. X cannot be 0. Now this doozy here. 7 over the 4th root of x to the 3rd.
Couple more minutes.
All right. 7 over the 4th root of x to the 3rd. All right. That's going to be 7 or 7 over 1, if that helps. 7 or 7 over 1 times 1 over the 4th root of x cubed. Nice save there. All right, 1 over the 4th root of x cubed. All right. Now, 7 over 1 is just 7. All right. So the 7 can pop out easily. Any factor on the top can pop out easily. Right. It's that whole negative exponent trick that you got to be kind of careful. But the 7 on the top, as a factor at the top, that pops out as a 7. All right. Times, what's this? It's going to be x to the what? X to the negative 3/4. Why x to the negative 3/4? Why negative up here? Why negative? Because this is in the bottom. It's a factor of the bottom. Why the 3? Because that indicates the power. Why the 4 down here? It indicates 4th root. 7x to the negative 3/4. And then for the restrictions, look over here in this radical form over here. All right. Let's go through these cases. Can x be positive? Cubing a positive gives a positive. 4th root of a positive is positive. Divided by a positive, no problem. Positive values for x, not a problem. Can x be 0? That bottom turns out to be 0. Answer is no. Maybe I shouldn't use x to mean wrong here, but you get the idea, right? What about x being negative? How about that? X being negative. Well, the cube of a negative number is negative, but then the fourth root of a negative number, that's no good. Gotta be positive. X has to be positive. 7x to the negative 3/4. 7x to the negative 3/4. All right. This is your bread and butter in calculus. Because trust me, if you want to take the derivative or the integral of something like this guy, you're going to want to write it out like this and not like in the radical form. Because we have nice rules for differentiation and integration if you're dealing with these kinds of expressions. Rewriting expressions is a key part of calculus. For some people, that's the tricky part. Next up, let's use the rules for exponents and radicals to simplify expressions. More complicated expressions, like these. Okay, next time.
But let's take a break. Well-deserved break, all right? If you use the restroom, please mute. Okay, I'll see you at 8:38. I'll see you at 8:38. All right. All right. Okay, first off, before we proceed, any questions before we proceed? Any questions before we proceed? All right, putting on the chat. So chatting here. All right. Okay, any questions before we go on? Any questions? All right, so I've resumed. Okay, so let's simplify expressions. All right.
Thing here. 3 over negative 2x squared all to the negative 4. We want to simplify this expression, make it look nicer, and we want only positive exponents in our final answer. So non-positive exponents, that is exponents that are negative or 0, are not allowed in the final expression. So if you have exponents in your final answer, they better be positive. All right. Now, first off, I don't like the fact that there's a negative exponent up here. So how can we rewrite this expression as something equivalent where we have a positive 4 as the exponent? What do we need to do to turn the negative 4 into a positive 4? We have to take the what of the base here. We have to take the reciprocal of the base here. And that's this rule over here. Number 8. If you have a fraction raised to a negative exponent, you can change that to a positive exponent if you take the reciprocal of the base. So the exponent goes from negative 4 to positive 4. We have to take the reciprocal of the base. Take the reciprocal of the base. Okay. If you're going to take the opposite of the exponent. By the way, right off the bat, there's a hidden restriction. 0 is an illegal value for x over here. We should technically note it over here. But usually what we do is we save it for the end. Okay. So when we note the restrictions, the domain restrictions at the end usually. But technically, we have a hidden restriction right here. When you pull a stunt like this, you might end up hiding restrictions. Things involving reciprocals, negative exponents, things like that. All right. Now, and different students might perform the operations in a different order, okay? But we basically have a quotient or a fraction being raised to a power or exponent. This exponent can be shared, all right? That's basically rule 5. Okay? If you have a fraction raised to an exponent, the top and the bottom share the exponent. In restriction note over here. All right, so we have, so this up here is the top to the 4th over the bottom to the 4th. So we have I'll make this bigger here, right? negative 2x squared all to the fourth over 3 to the fourth, okay, with this hidden restriction. And then over here, we have now the power of a product raised to a power or exponent. Again, like with the quotient, we share the exponent across the factors. Remember, we need grouping symbols around the negative 2. Okay, because if you just write this, it turns out you're going to be wrong. All right, so don't do that. Okay, so it's the fourth power of negative 2 times the fourth power of x squared over, and then 3 to the fourth is 81. Okay, what is 3 times 3 times 3 times 3? What's 3 to the fourth? Well, 3 times 3 is 9. 3 times 3 is 9. 9 times 9 is 81. All right. All right. Now the fourth power of negative 2, right? Well, the fourth power of a negative number is positive, right? You can even break this up further as negative 1 to the fourth, okay, times x squared to the fourth. Whoops, I'm sorry. Times 2 to the fourth, okay? So if you're concerned about the fourth power of negative 2, you could write it as the fourth power of negative 1 times the fourth power of 2, okay? The fourth power of negative 1 is just 1, right? 2 to the fourth is 16. 2 times 2 times 2 times 2. Similar logic here. All right. Now, the fourth power of x squared. When you raise a power to a power exponent, what do you do to the exponents? That was rule number 3 here, law number 3 here. You raise a power to a power or exponent, you multiply the exponents. 2 times 4 is 8. So we have 16, x to the 8th over 81. And this is simplified because remember, 16 is 2 to the fourth, 18 is 3 to the fourth. There are no good factors in common. By good factors, I mean anything besides 1 or negative. So we cannot reduce 16 over 81. But remember, we have the hidden restriction. Don't forget that 0 is illegal for x. If 0 is illegal for x over here, and it was, because it would lead to a division by 0, then 0 is still illegal. But since it's a hidden restriction, it's not evident, we really should write it. So this expression here, I'll put this in green, this expression here is equivalent to this expression here, together with the hidden restriction. All right.
Okay, so any question? I'm doing some chatting here. Any questions? Any questions? Now, bear in mind, if x starts in the numerator, remember, it's okay for the top to be 0. 0 divided by 1 is 0. 0 divided by 2 is 0. 0 divided by 0 is a problem, as Siri pointed out. But you can have 0 on the top. You cannot have 0 on the bottom. Bear in mind, 0 to the negative 1 is also messed up. Any questions? Any questions? Okay, so I'm noticing, yeah, a lot more questions about math than last time. Yeah. A lot of people got stuck in these parts. All right, anything else? Any other questions? Okay, we're still recording. Good, we're good. All right.
Let's do a second simplifying problem. Let's simplify this expression in x. Now, if I were to ask you right now, what is the value of this when x equals 3? You might be going, are you punking me? Are you kidding me? No, simplify the expression and you can do it quickly. All right, again, non-positive exponents are not allowed in the final expression. Now, first of all, we might want to express these factors in the top and the bottom as nice powers of x. So for example, x is going to be x to the first, right? The square root of x is going to be x to the 1/2. Down here, we have x to the 7/2. And what is x to the 0? X to the 0 is 1. Although 0 to the 0 is controversial. And while we're at it, if you look at this original expression, we might want to consider the restrictions. What are the restrictions on x right now? Can x be positive? Looks good. Square root of a positive. The square root of a positive is fine. Yeah, positive values for x look good right now. What about 0? 0 to the 7 halves. For example, the square root of 0 is 0. That's going to be no good. So 0 will be no good for x. What about negative? Square root of a negative number, no good. Either here or, as it turns out, the x to the 7 halves would have a problem with that also. So x cannot be negative, which means that we need x to be positive in order for this expression to keep it real. The restriction is going to be x has to be positive. Okay. Once again, x is x to the first. The square root of x to the 1/2. X to the 7 halves copies over. X to the 0 is 1. And we can ignore this at this point. Now, up here, how do you multiply powers of x? To multiply powers of x, you do what to the exponents? You add them. If you wish, you could do this work on the side. What is 1 plus a half? That's 2 halves plus 1/2, right? 1 is 2 halves. 2 halves plus 1/2 is 3 halves. So the exponent here is 3 halves. Again, I do recommend side work instead of trying to micromanage over here. Do side work like this if you have to. We have x to the 3 halves over x to the 7 halves. I'm ignoring the hidden restrictions for now. When you divide powers of x, what do you do to the exponents? That's rule 2 over here. When you divide powers of x, you subtract the exponents. What's 3 halves minus 7 halves? That's going to be negative 4 halves, also known as negative 2. It's got to be in this order. 3 halves minus 7 halves is negative 4 halves. Okay, right? 3 halves minus 7 halves. It's going to be negative 4 halves. Okay. Although do side work. Don't micromanage it. Right? I note here that the hidden restriction x being positive, it turns out that when you perform this division, that's when you hide the restriction. Though it's not always clear. So I would say consider the restrictions either at the very beginning or consider the issue at the end. Okay, but anyway, we end up with x to the negative 2. 3 halves minus 7 halves is basically negative 2. We have x to the negative 2. Now, we're not done yet. We're not done yet, right? X to the negative 2, that looks nice, but remember, non-positive exponents are not allowed. Non-positive exponents are not allowed. Negative exponents are not allowed in your final answer, right? What is x to the negative 2? Look at number 7, law number 7 in reverse. X to the negative 2 is what? It's going to be 1 over x squared. Where, again, x is restricted to be positive. So then the given expression, which was this, is perfectly equivalent to this over here, 1 over x squared, if x is positive. Because only positive real values for x were illegal up here, therefore only positive real values for x are legal down here. So we're not allowed to plug in x equals 0, certainly, but not even x equals negative 3 or negative 5. Now, I asked you way up here, what is the value of this expression if x equals 3? It's hard if you look at this, but if you look at the simplified form here, it's easier to plug into x here. All right, what is the value of this when x equals 3? It's going to be 1/9, right? 3 is a legal value for x, 3 is positive. You plug in 3 for x, you get 1/9. Piece of cake. So if you want to evaluate expressions, it's often in your interest to simplify an expression like that into a simpler expression in terms of x, and you can get this very quickly. There's a purpose to simplifying. Also, of course, in calculus, if you're asked to differentiate this or integrate this, you'd much rather do it to this guy here. Simplifying is your friend, but sometimes it takes some work. All right, I have some footnotes for your side interest. Until then.
All right, any questions? Whoop. Any questions? I think I may have, okay. Any questions?
Let's do it.
Elaborate on
I have some
footnote.
footnotes.
Okay, so again, the footnotes, don't worry too much about them. Oh, you mean this one here, like x is a 2, 6? Yeah, that's interesting. Okay, and in fact, I talked with the pre-calc author Ron Larson about this. See, what's the domain for this? Well, if you read it as doing the square first and then the 6th root, all right, well then you're all good, right? Because x squared, as long as x is real, x squared is never negative. So the domain is all reals. Okay, so 6th root of x squared, domain is all reals. It's all good. Okay, but, okay, if you do the 6th root first, like over here, right? Like over there, then you need to make sure that x is not negative, right? Okay, but if you do the 6th root first, x has to be non-negative in order for that to work, and the squaring is not a problem. So if you have x to the 2 6th, the domain depends on which you do first, and that's why it's confusing. All right, I don't like getting into this issue, and technically you do see it once in a while when you do your work, but don't freak out at this. All right, but don't worry, we're not gonna worry about this issue too much, although it's a legitimate source of some concern. It depends what's done first, and different books do it different way, do different ways. All right, anything else? Anything else?
So what is a domain?
A domain is a set of all, okay, yeah, that's a chapter 1 issue. The domain is the set.
No, like what is a domain for this example? If you can get different, like, because on the first one, it was all real numbers. And then on the second one, it depending on the way you interpret,
Right.
It will be different, right? So,
okay, so first of all, let me define. The domain is a set of all real values of x, in this case, for which the result is real. All right, so again, sort of reiterating, when we had the 6th root of x squared, you take any real value, you can square any real number, the result's real. Okay, real and non-negative, right? X squared is non-negative. If you square a real number, the result is non-negative, okay? Which means the 6th root, it's guaranteed you're taking the 6th root of a non-negative real number, you're good. Now the problem with this second form here is that you're starting by taking the 6th root of x. If x is negative, you're in danger right here. And in fact, we say game over right there. If you're trying to take the 6th root of a negative number, we say game over right there. So the order does matter in terms of whether negative values of x are legit or not. And different books define x to the 2 6 in different ways. Fortunately, in the problems you deal with, your results are not affected by that distinction.
oh, okay. Got it. Thank you.
Watch out for those footnotes. It's those details that I love mulling over, but students go, what are you talking about? So be careful. One problem with the footnotes is that if you read the footnotes, maybe you're a very good student reading the footnotes, but you're in danger of confusing yourself, because often a footnote is an issue that confused me. So I wrote the footnote as a way of organizing my own thoughts. All right. So folks, if you didn't get that, don't worry. But the footnotes are there for your side benefit. All right.
Until then. Hi, everyone. Let's talk about section 0.6, various types of expressions in X. Before, we classified numbers. Now, let's classify expressions in X.
Okay, let me restart with the captions.
Before, we classified numbers. Now, let's classify expressions in X, let's say. All right. First of all, what's a polynomial? These are things that you studied back in your Algebra 1 and 2 classes. Here's the bad news. The formal definition for a polynomial looks like this. And seriously, in the Math 200 level class, you better be prepared to write a form like that. But let's come back to this later. Let's do some examples first, okay? Let's do that. All right. So let's do an example first. Example. this is an example of a polynomial. Okay, let's try to remember the various terminology here. All right, so here's a polynomial. 4x to the third minus 5 halves x squared plus 1. Notice that the exponents here, make some comments here. Notice that the exponents here are non-negative integers. Non-negative integers. The exponents on x, I should say. It's okay to have a messed up number like pi, all right? But you cannot have x to the pi. You can have pi, but not x to the pi. All right, so the exponents on x, the 3, the 2, there's actually a power of x here. X to the what is 1. X to the what is 1. X to the 0 is 1. So you could think of 1 as 1x to the 0. The exponents on x are all non-negative integers. The highest exponent on x, is the degree. Okay. Assuming that's being written in this descending powers form, which I indicate over here. I'm assuming the polynomial is written in this descending powers form. All right. But as it stands, the highest exponent in x indicates that's a third degree polynomial. All right. The leading coefficient is the 4 here. That in brown. The leading coefficient is going to be the 4 here. Now, the degree and the leading coefficient are both obtained from this here, which is called the leading term. The leading term is 4x to the third. It's the term containing the highest power of x, the x to the highest exponent, the degree. 4 is the leading coefficient, 3 is the degree. So the leading term is very powerful. If you tell me the leading term for a polynomial, I already know a lot about the polynomial. We'll see that in chapter 2. And then on the other hand, here's this little guy here. Constant term is 1. If you don't see a constant term, okay, something that a number without an x to an x or an x squared next to it, if you don't see a constant term, then it's 0. So if we didn't have the plus 1, the constant term would be 0. All right. Now, it doesn't matter what order you order the terms in. This is ascending powers form up here. But you can reorder the terms, and you'd still have the characteristics that it would be a third degree polynomial in x. 4 is still the leading coefficient. But be careful, because if I ask you, what's the leading coefficient on this polynomial? The leading coefficient is still the 4. The leading coefficient is still the 4. 4x cubed is still the leading term, right? Even though it's written at the right end here. That's why descending powers is often more convenient, because then you can quickly tell the leading term is the guy on the left. All right. The polynomial fits this ugly form here, where n is the degree. So I'm doing this bit by bit, right? I'm gonna blow this up a little bit. Okay. In blue, the degree up here is 3, all right? Degree equals n, which is 3 in our example. All right. Now, here's the thing. So this is of this form, where the leading term, 4x cubed, put that in dark brown, right? The leading term, 4x cubed, is a sub n x to the n, right? A sub n is the leading coefficient, that's in light brown. Okay, 4 is the leading coefficient, that's this a sub n guy. Remember, n is the degree. So the coefficients are a sub 0, a sub 1, a sub 2, and so on up through, in this case, a sub 3. That's going to be the leading coefficient. It's the coefficient for the x to the third term. And then the constant term, 1, that was in purple. the constant term 1 is going to be a sub 0. Because remember, you can think of 1 as 1x to the 0. So it's the 0th degree term. So this polynomial, if you want to expand it out, you could write it as, so here I'm literally expanding it out. I'm writing it out, and I'm indicating the missing term, 0x. There's no x term in here, so the corresponding coefficient is 0. I'm putting in the missing term. Sometimes we do want to indicate the missing term. So here's the polynomial written in descending powers, all right? It follows this format. Where the coefficients are, let's read off the coefficients. In fact, we might want to go in reverse here. We might want to go in reverse. All right, so the constant term, the 1 here, is a sub 0, okay? It does count as a coefficient. Now, a sub 1, okay, is going to be the coefficient on x. So here's this term, 0x. The coefficient on the x term is 0. That's the value for a sub 1. A sub 1 is 0. This is like the data sheet for this polynomial. If I know that's a polynomial in x, I know the degree, I know these coefficients, I'm set. A sub 2, what is the coefficient on x squared? Be careful. What is the coefficient on x squared? It's negative 5/2. So a sub 2 is negative 5/2. In the generic form, we put plus signs here so that if the coefficient is positive, well, we see plus. If the coefficient is negative, we see minus in the final form. The leading coefficient, I always put this in brown, I guess, a light brown. The leading coefficient, the 4 here, that's a sub 3. In general, the leading coefficient is a sub n. If I had a 10th degree polynomial, then the leading coefficient would be a sub 10. In this case, it's a 3rd degree polynomial. The leading coefficient is a sub 3. So that's the data sheet of coefficients for this polynomial in x. So if I have a polynomial in x and you care, then if I tell you what a sub 3, a sub 2, a sub 1, and a sub 0 are, you're set. You can construct the polynomial and make it look a little bit nicer, like up here, without all the marks. Basically zap the missing term. So a constant like 1 or 7, these guys are themselves polynomial, but they're 0th degree. You can think of 7 as 7x to the 0. It counts as a 0th degree polynomial, albeit with just one term. The guy up here has 3 terms, as it's written, 1, 2, 3. You don't count the missing terms with 0 coefficients. The key terms are separated. Okay, the number of terms are indicated by the number of primary plus signs and minus signs plus 1, right? So here, we have an implied plus sign in front. We have one term. I should erase all this. There's so much going on here. All right, so we have an implied plus sign here, all right? We have 3 terms. The 3 terms are 4x cubed, negative 5x squared, and positive 1.
Negative 5/2 x squared.
So 3 terms. Okay. And each term corresponds to a primary plus or minus sign in front. There's an implied positive sign in front here. All right. So what's more general than polynomials? All right. We'll talk about that later on. Now, I mentioned the number of terms. What are some things we care about with a polynomial? All right. So if I have a polynomial and you care, all right, then what are some things that you might care about the polynomial? You might care about its degree, the highest exponent on x, and you might care about the number of terms. By the way, when I went over this stuff, I was basically going over the definition of a polynomial, all right? So, in fact, I'll go over this before I go on to the categories, right? So what's a polynomial? Let n be a non-negative integer. That's going to be the degree. An nth degree polynomial in x, written in descending powers of x, has the following general form. This over here, where the leading coefficient, by definition, cannot be 0. the a sub 1, a sub 2, etc. These guys are the coefficients. They're the numbers in front of the powers of x. And we're going to have real numbers as coefficients. Although later on, in very high math, they can be imaginary. Again, the leading coefficient must be non-zero, although the others could be, right? I mean, maybe 4 is the leading coefficient, and if all these other coefficients are 0, then 4x cubed is your only term. You have a one-term polynomial called a monomial. Okay, the last guy is a constant term. If you don't see one, it's 0, right? Right. Only non-negative integers as exponents. So we went over the definition of a polynomial and the anatomy. What are ways of categorizing polynomials? Well, we can categorize them by degree. Now, 0 itself is a polynomial with no degree. He's too weird, all right? But a non-zero constant like 1, 2, 3, 7, pi, your SSN, negative 12 thirds, well, negative 12 fifths, okay? The non-zero constants, they have degree 0, because you can think of 7, for example, as 7x to the 0. A first degree polynomial will be linear, like 3x plus 4. Second degree, quadratic, like 5x squared minus x plus 1. Remember, the degree corresponds to the highest exponent on x in the descending powers form. So don't have any messed up things like all squared or something like that, because then that might make the degree more confusing. Here's an example of a cubic. See, the highest exponent on x is a 3 in the descending powers form. And then these are more rare. 4th degree is quartic, 5th degree is quintic. Okay, but these are good terms to know. Constant, linear, quadratic, and cubic, which will tell you the degree of the polynomial. Also, categorizing polynomials by number of terms. So a polynomial with just one term, like x to the 5th, so the leading coefficient is the only non-zero coefficient. That's called a monomial, like a monocle, which rich people used to wear. That's why I have a monocle. All right, a binomial, 2 terms, like a bicycle has 2 wheels. This is like a pi bicycle. Oh, wow. That's why I'm not an art major. All right, so a 2-term polynomial is a binomial. It can be of any degree, except maybe 0, because that's like just a constant. Okay, a 3-term polynomial is a trinomial. 5x squared minus x plus 1. So this here, I call a QT. That's not an official term, but that here, this guy here is an example of a QT. Why? What degree is this? 5x squared minus x plus 1. The degree is 2. Therefore, it's called a quadratic polynomial, or just a quadratic. A QT is a quadratic based on the degree. How many terms? 3 terms. Quadratic trinomial. Like a tricycle has 3 wheels. I'm not going to draw a tricycle. Quadratic trinomial. And what do we do with quadratic trinomials? Guys like these, back in your Algebra 1 class, what was the frustrating thing you did with these guys? You factored them. Maybe using guessing or something like that. We're going to factor quadratic trinomials and review that. Okay. Now, before we go on to the more general expressions, a lot of people forget how to square binomials. The square of a plus b is not, I repeat, is not. I better put this in red. Sorry. Okay, let's get in here. There we go. Not. The square of a plus b, am I making my point? The square of a plus b is not a squared plus b squared. So all that effort. The square of a plus b is not a squared plus b squared. It's this thing here, all right? So if you take a plus b, what does squaring this binomial mean? Well, you take the square of something, you take this guy, and you multiply by itself. And then you apply what four-letter acronym? It's really the distributive property, but you apply the FOIL method. And you get a times a is a squared over here. B times b is b squared. But don't forget, all right. It's true that a times a, the product of the first terms, is a squared. It's true that b times b, the product of the last terms, the L, is b squared. But don't forget, the product of the outer terms is ab, right? O, I for inner, the product of the inner terms, BA. But these are equivalent terms, right? AB plus BA is 2AB. And a lot of students forget that 2AB. The square of a plus b is not a squared plus b squared. It's this thing. It's this trinomial. Lots of memes for this. First of all, if you don't see why that is, look at this. Look at this square here. Side length a plus b, side length a plus b, all right? The area of this big square is the sum of the areas of these little squares and rectangles. The area of the yellow rectangle, a times a is a squared. The area of the green rectangle, b times b is b squared. The blue, b times b is b squared, that's the area of the green square here. The blue rectangle here, a times b is ab. The blue rectangle here, b times a is ba or ab. The total area of the big square is a squared plus 2ab plus b squared. You can extend this idea to 3 dimensions, where you get 4 terms in the expansion. 4 dimensions, raised to the 4th power. That's called a tesseract, like in A Wrinkle in Time. You get 5 terms in the expansion. In chapter 9, we're going to talk about the binomial theorem, where we're going to take a plus b, maybe to the 10th, and find a very quick way of writing it out, or a pretty quick way of writing it out. See here, the square of a plus b. Don't forget the 2 skinny rectangles here, right? The 2ab there. Some more memes. I got these from, I guess, Facebook or somewhere. Read it. And this one here. And folks, that's not blood. I just assumed it said, hey, Ken, is that blood? No, it's not blood. It's a cloud. Please, it's not blood. It's a cloud. She's not that vicious. All right. So the square of a plus b, it's not a squared plus b squared. What is it? It's a squared plus 2ab. Don't forget those little rectangles, right? Don't forget the little rectangles from this guy over here, right? Over here. Remember, in the FOIL method, product of the first terms, a times a is a squared, that's fine. L, product of the last terms, b times b is b squared. But don't forget, product of the outer terms, a times b. Product of the inner terms, b times a. Here's FOIL, right? A times a is a squared, that's the F. B times b is b squared, that's the L. Product of the first terms, product of the last terms. But don't forget, in bright red, product of the outer terms, a times b. Product of the inner terms, b times a. That's a 2ab. And then likewise, the square of a minus b is a squared minus 2ab plus b squared. These two guys are referred to as PSTs. For what? Do you remember? Perfect square, trinomials. Perfect square trinomials. They factor. Factoring is when you reverse the multiplication, reverse the squaring. Factoring is going this way, make it more, in this case, make it more compact, all right? Factoring it like this, as a product or a square here. Perfect square trinomials. So the square of x plus 3 is x squared, right? We also have the 9. The square of 3 is 9. But don't forget, 2ab, twice the product of the 2 terms, right? So what's that middle term here? Okay, don't miss the middle term. Don't miss the middle term. How do you get the 6x, right? It's twice x times 3. It's twice the product of the two terms. Twice x times 3 is 6x, the 2ab term, right? Or in this case, it's the negative 2ab term if you have a minus sign there. All right. Next, we're going to talk about more general expressions.
Okay. Any questions? Any questions about polynomials? All right.
Hi, everyone. So similarly to what we did with the numbers back in section 0.1, let's do a Venn diagram for various types of expressions in X. So we've talked about polynomials, the simplest kind, and that included numbers, like real numbers, like 1, pi, negative pi, and so forth. Numbers, constants, count as polynomials. Also things like x to the 7th plus x, or that 4x cubed guy we saw earlier, all right? Those are polynomials. Now, all polynomials are also rational expressions, because you can always put polynomials over 1 and get a rational expression. A rational expression can be expressed as a polynomial over a polynomial that's not the zero polynomial. The simplest rational expression that's not a polynomial is 1 over x. 1 over x is not a polynomial because even though 1 over x can be written as x to the negative 1, you're not allowed to have negative exponents on x for a polynomial, but you can have negative exponents on x, negative integers on x for a rational expression. Every rational expression is also an algebraic expression, but you also get guys like these, like the square root of x or the cube root of x. The square root of x can be written as x to the 1/2. This is not a polynomial because you need integer exponents in order to have a, in fact, non-negative integer exponents on x to have a polynomial. Again, 1/2 is not an integer, so it's not, so x to the 1/2 cannot be a rational expression because you're not allowed to have exponents like 1/2 or 1/3 on x for a rational expression. So the square root of x is in some ways the simplest algebraic expression in x that is not rational, or for that matter, a polynomial. Now, beyond the algebraic, now we're going to focus on algebraic expressions in chapters 0, 1, and 2. Then in chapter 3, we're going to start talking about exponential and logarithmic expressions, like 2 to the x, or ln of x. These are not algebraic. And in chapter 4, our old friends, sine of x, cosine of x, and so forth, even inverse sine of x. Those are not algebraic. We're going to see these in chapters 3, 4, and beyond. All right. So a quick recap. A rational expression in x can be written as a polynomial in x over a polynomial in x that's not 0. Bear in mind, you can have these expressions in y or z or whatever, but let's say x for now. Here's some examples. 1 over x is the easiest. This is more complicated, but you still have a polynomial over a polynomial. This is a rational expression in x. And again, every polynomial is a rational every polynomial in x is a rational expression in x because you can just stick the guy over 1. An algebraic expression is allowed to have non-integer rational exponents like 1/2 or 1/3 or 5/7. The cube root ultimately becomes a 1/3 as an exponent, right? I call this expression algebraic. Some books object to the pi there, but I call this expression algebraic. It's kind of like a rational expression where you're allowing for exponents on x like 5/7 and 1/3. Bear in mind, you can always have weird things like 3 to the pi. If it's all constant, that's always fine. Well, although, again, some books quibble for algebraics, but I say that's fine even for an algebraic expression. All right, so a taxonomy, in a way, a hierarchy of expressions in x. Next up, how do you factor QDs, quadratic trinomials, and more?
All right, so let's go to that
Hierarchy of
hierarchy. Any questions about that hierarchy? It's not like the integers, rational numbers, right? Okay, going to the final part, a bit of factoring. And then the plan is that after this last video, we're not going to make it all the way through chapter 7. After this last video, you can go through 0.7 number 2, I believe, on the homework, if you're keeping up with the lectures. Although, of course, feel free to work ahead. I'm not teaching you bizarre Martian algebra. That's brand new.
Expressions in X. Next up, how do you factor QTs, quadratic trinomials, and more? Hi, everyone. So this is a big topic back in your Algebra 1 class, factoring polynomials. Now, I don't have time to review all this in our class, but I want to give you all the resources you need. Alex will help a lot if you need review. ALEKS. Maybe the tutor Alex, but ALEKS. I don't know if there's a tutor Alex. All right, anyway, let's do some examples. Let's go straight to some examples. Right? If you see something like 8x plus 6, often the first thing you want to factor out is the GCF, the greatest common factor or divisor. All right, so in this case here, 8x plus 6, if you want to factor 8x plus 6, the largest thing that goes into 8x and 6 is 2. You factor out the 2. When you factor, you do what? D word. When you factor, you divide. 8 is 2 times what? 8 is 2 times 4. What did you do with the 8 and the 2 to get the 4? You divided. 8 divided by 2 was 4. When you factor, you divide. That's a critical theme. When you factor, you divide. So when you factor out a 2, you divide 8x plus 6 by 2. 8x divided by 2 is 4x. 6 divided by 2 is 3. So when you factor, you have to factor out the GCF. It might be all at once, it might be piece by piece, but eventually you have to factor out the GCF. X to the 5th plus x to the 3rd. How do you factor that? You factor out the power of x with the least exponent. What's the least exponent? 5 or 3. Which is further to the left on the real number line? Well, it's going to be the 3. There are other numbers in here, but I'm pointing out 3 is less than 5. It's further to the left. So when you factor this, you want to factor out x to the 3rd. That's your GCF. When you factor, you divide. All right. Now, what is x to the 5th? I'll do this in red. What is x to the 5th divided by x to the 3rd? We start here with x to the 5th. In a way, we're taking out x to the 3rd. What's x to the 5th over x to the 3rd? X to the, when you divide powers of x, what do you do to the exponents? You subtract them. 5 minus 3 is 2. That's why you have x squared over here. And then the x cubed divided by itself, don't worry about the 0 issue. X cubed divided by itself is 1. All right, so you need that 1. You can think of it as a necessary placeholder. X cubed divided by itself is 1. A lot of students forget the plus 1. We do need it. All right. And then the x squared plus 1 is what we call prime over the reals. There's no way of breaking down or factoring x squared plus 1 any further where you're just using real coefficients. And 1 times doesn't count. All right. Sometimes it helps to factor out a negative GCF. Although you might want to tear it apart bit by bit. So for example here, if you wanted to factor negative 8x to the 5th minus 6x cubed, you might want to start by factoring out a negative 1 first. The GCF is larger than that, but you might want to start out by factoring out a negative 1. When you factor out a negative 1, indicated by this opposite sign here, when you factor out a negative 1, when you factor, you divide. Well, when you divide both these terms by negative 1, you're flipping the signs. There's an implied positive sign in front of the 8. And then you factor 8x to the 5th plus 6x cubed. 8 and 6. What's the greatest common divisor? The greatest common factor between 8 and 6? It's 2. What about the x to the 5th and the x to the 3rd? We just did this. What's the biggest thing in a way that divides both of these nicely? It's the power of x with the least exponent. It's going to be the x to the 3rd. So 2x to the 3rd, or you could say negative 2x to the 3rd, is going to be the GCF. when you factor, you divide. 8x to the 5th divided by 2x cubed is 4x squared. 6x, right? 8x to the 5th divided by 2x cubed. We've already taken care of the sign issue. Okay, that's going to be 4x squared. 6x cubed divided by 2x cubed is 3, positive 3. 4x squared plus 3, that turns out to be prime. If you're not sure about that, we'll discuss that later on. But in Algebra 1, you did not break this down any further. Be careful. Can you factor this like this? Oh, I see that x is a common factor of the base here. Let's take them out. Ah, that doesn't work. Not equivalent. So here's the thing. When you factor out the x, you better put grouping symbols because the 5th power applies to all this stuff. And then both these factors, the x and the x squared plus 1, share the 5. So if you're going to take out an x, don't forget the 5 goes along with it. When in doubt, use grouping symbols. We're basically appealing to this rule here. xy all to the n is x to the n. In this case, x to the 5th. Y to the n. Y is x squared plus 1. All right, factoring formulas. You're going to need to know these. Be able to factor a PST. We're reversing the squaring rules from before. Remember the squaring rules from before? When we squared a binomial? Factoring reverses the multiplication rules, like FOIL and a plus b all times a plus b, right? When you square the a plus b. This is factoring going in reverse, reversing that rule. Right, so you can go from here back to here, expressing a PST as the square of a binomial. Now, we don't factor a sum of two squares using a general rule. We don't have a general rule for factoring a sum of two squares yet. We don't factor a squared plus b squared as it stands yet. But we do factor a difference of two squares. A squared minus b squared can be factored as a plus b and a minus b. If you don't believe me, FOIL this thing out and you'll get a squared minus b squared. If you want to check a factoring rule, take the result here, multiply it out, see if you get the left-hand side. You can check your proposed factoring rule. Okay, now you may not have seen these before. All right, factoring the sum of two cubes and the difference of two cubes. How do you factor a cubed plus b cubed? We do factor these, even though we don't factor the sum of two squares, with a general rule yet. Okay, a cubed plus b cubed, also a difference, a cubed minus b cubed. Bottom line is you end up with these guys over here. If you don't believe me, distribute like crazy, okay, simplify, and you'll get the left-hand sides. All right, but what's a way of remembering? All right, when you factor a sum or difference of two cubes using these rules, on the right side, you're going to get a binomial factor and a trinomial factor, a two-term guy and a three-term guy, right? Now, the binomial is pretty obvious. When you factor a cubed plus b cubed, you might guess that a plus b is a factor, and you'd be right. If you factor a cubed minus b cubed, you might guess that a minus b is a factor, and you'd be right. Now, notice, I'll put this in blue here. When we go from here to here, the sign stays the same. S for the same sign. Whatever the sign is here, that's the sign there. What about the signs in here? Focus on the signs, all right? Here we go from, I better put this in, let's see, turquoise. Plus to minus over here it's minus to plus. So for this sign over here, it's the opposite of what we got for both the binomial guy and the original. Over here, always a plus sign over there. AP, always plus. So the signs on the right side go SOAP. Same sign, opposite sign, always plus. SOAP. My colleague Larry Foster likes to use SOAP. Well, I hope he likes to use SOAP. He's a clean guy, right? Okay. You just have to remember this. Oh, and also, this is not a PST over here. there's no 2 there. I know you're used to a 2 being there because the PSTs have 2's in front of the AB term, all right? But there is no 2 in front. So be careful. Know your signs, and there is no 2 or negative 2 in front of the AB terms. In fact, the trinomial factor tends to be prime. The trinomial factor does tend to be prime. All right, I'm assuming you've already factored out the GCF of the whole thing. Remember, if there's a GCF that's not 1 or negative 1, you got to factor that whole thing out anyway. Eventually, it could be in pieces. All right, same, opposite, or different, always plus. The sign's on the right side. There are many other factoring rules, and there's a handout I have. Okay, so review the handout. It's in my online notes. Can you do these 10 factoring problems, actually 12 factoring problems? The last 2 involve sum or difference of 2 cubes, right? But can you do these 12 problems? I have these 12 problems, and I have solutions in my notes. Practice those. Alex can help.
That's not homework, but good to
Next,
practice.
even more factoring.
All right, but that's for next week. All right. All right. So that's the lecturing for today. A lot of stuff today. All right. For some of you, I'll see you on Tuesday, or I'll communicate with you on Tuesday. I do check email though, even over the weekends. All right. Any questions from the class before we take specific questions on homework, things like that? Okay. Any general questions? We'll continue with factoring next time. And again, if you're following the lecture, you can go through 0.7, number 2 on the homework if you're keeping up. If you're keeping up, feel free to work ahead. Any general questions from the class? All right, good luck, everyone. Don't procrastinate on the homework. Now, at this point, I'll take public questions and then private questions. I'm still recording, all right? So while I'm still recording, are there any questions that people would like me to work from scratch, for example? Otherwise, if everyone wants to go private, I'll go. If everyone wants me to stop the recording, I'll stop the recording. But anyone want to do a public problem? Someone asked for. By the way, I'm done with the class, but I'm now doing homework questions. 0.51e. Would you like to? Is it okay if we do that publicly, or would you rather have it go privately? Public? Okay. So I'll do this publicly. All right. So let me sort of set myself up then. All right. Let me get my little marking boards here. Okay. On-screen signs. All right, here we go. Okay, so I'm going to grab some of my, okay, I'm going to go ahead and grab, these are like my whiteboards. All right. Okay, 0.51e. And finally, I can do this now that I'm not just playing the videos full screen anymore. I can actually see the homework. I haven't memorized them. Although they're mine, I haven't memorized them. All right, here we go. So 0.51e. Oh yeah. Every semester, people ask me about this one. All right, let's do it. And different people can do it different ways, but let's try to do it efficiently. All right. Okay, so over here, this one over here, right? Oh, I'm gonna go ahead and duplicate this. Right. Okay. All right. Okay, doing this one over here, right? All right. Okay. Okay, in the beginning. Actually, right off the bat, I have an efficient thing here. Okay, we have root 2 times root 9 divided by root 3. Okay, the root 2, I'll copy that. But then the root 9 and the root 3, I can do some division here, right? So we have the root 9, we have the root 3. We can go ahead and do this first, okay? We can do a little bit of canceling. Root 9, what is root 9 divided by root 3? It's root 3. I can kind of do this. This is really what's happening, all right? So I can think of this as root 2 times root 3. I know that sticklers might say, well, shouldn't we work out the top first? You can. You'll get root 18 on the top, okay? But we start off with this. All right. And then what is root 2 times root 3? That's root 6. I'm focusing on this first term here. So this thing here is root 6. All right. But then we also have that plus root 2 at the end. I should have put I'll do that in red. Don't forget there's also the plus root 2. Some people work better step by step. Other people should go all the way. Write this all out. All right. So we get root 6 plus root 2. That's one of the more efficient ways of doing it. Root 6 plus root 2. Okay, I do have the answers, by the way, also. Let me grab the answers here. Right, root 6 plus root 2, which is not root 8. Okay, remember, you're not allowed to add radicals like that. Root 6 plus root 2 is not root 8. Okay, you can multiply radicals nicely, but you cannot add radicals nicely in a similar way. Any questions thus far? Any questions thus far? I see that pen. Hold on a second. By the way, some books do something weird. They do something like they okay, so I have those. All right, let me open this up again. Okay, some books do something kind of weird. They factor out a root 2. Okay, which is kind of weird. And if you do that, you don't have to do this, but some books do this. All right. They try to factor out the root 2, and they get root 2. When you factor, you divide. Okay, so we're kind of going backwards almost. Root 3 plus 1. Some books do that. I don't require that. All right. But any questions? Any questions? So you have questions here. Okay. Oh, you're welcome. Okay, chatting here. Okay, can you factor a sum or difference of 2 cubes? Like an example? Yeah. Okay, so we can do an example of that. I can stay here. Well, it might help if I have the let's see, where am I? Or we could do. Do you want to do ones? Maybe one of these, unlike this this sort of practice handout. Well, we can do one of these practice handouts. All right. Like K, for example. All right. Again, this is not homework, but I wanted people to look these over. Okay, so K, let's take a look at K. Okay, how do you factor x cubed plus 125y cubed? Okay, x cubed is a nice cube, and you might recognize that 125y cubed is a nice cube. All right, so what's the deal here? And again, I'll get the template. Oh, okay, I'll do this. Okay, and here's the rule. All right. Okay, so instead of a cubed plus b cubed, we have x cubed plus 125y cubed. So here's a way I might think of this. All right, so what's the sign? S for same sign. I have a plus sign here. I have a plus sign here. That's from SOAP, same sign. All right, and then I'm basically asking, what are the cube roots, right? The cube root of a cubed is a. The cube root of b cubed is b. What's the cube root of x cubed? Well, that's going to be x. X is the thing such that when you cube it, you get your x cubed. Now, what's the cube root of 125y cubed? I'll do this in, you might want this as side work. Okay, here's what you're thinking. So 125y cubed is the cube of what? What's the cube root of 125y cubed? 125 is the cube of 5. You should recognize that. Y cubed is the cube of y. So you agree 125y cubed is the cube of 5y. All right? And that's what goes over here. The cube root of the 125y cubed. Any questions about the binomial? All right? That's the a plus b piece. A is x, b is 5y. All right? And then what you do is you build off the binomial to get the trinomial. All right, I'll do this in blue. So here a goes to a squared, x goes to x squared. What about the sign? All right, S for same sign, O for opposite sign. We had plus signs over here, it's minus sign over here. AB, you take the product, x times 5y is 5xy. Okay, so minus the product of the two terms, x times 5y is 5xy. AP, always plus. B squared, B is the 5y over here. It's that second term here, right? You can ignore the sign. Second term here, 5y. What's the square of 5y? The square of 5y is 25y squared. Remember, you got to square each factor. All right. So that's my messy screenwriting, but I believe the answer conforms with that. Oh, wait. That's in my solutions. Okay. So here I did it organically, right? SOAP, S-O-A-P. But here in my solutions, it's typeset. All right. So again, x cubed is the cube of x. That goes here. Same sign. S for same sign. That's a plus sign. 125y cubed is the cube of 5y. And then for this guy, you square the a to get a squared. You square the x to get x squared. Okay, over here, opposite sign. Maybe I should do the signs on the bottom. Okay, first same sign for this guy. And then opposite, well, maybe I'll build off of here. Opposite sign for this guy, the minus sign. Then 5xy. Ignore this sign. Take the product of these guys, the x and the 5y, 5xy. Always plus AP. The square of 5y is 25y squared. The square of b is b squared. All right, any questions about that? Any questions about that? All right, again, I'm still recording. If you have a private question, let me know. All right. So I guess I see 0.1 number 6. Okay, again, right now everything's public. If you want to be private, let me know. Okay, 0.1 number 6. All right. Ah, yes. Okay. In fact, I might just go straight to the answer because it's a better typeset. Okay, the set R, set difference, -2. So I want the set of all real numbers except for -2. All right. And by the way, if I have the wrong problem, please let me know in the chat. Okay, sometimes I refer to the wrong problem. Okay, so this one, right? I'm gonna go straight to the answer because it has the better typeset. That'll help out a lot here. The answers. Oh, let me okay, let me go back here. So we're doing 0.1 number 6, right? Oh yeah, and that's the answers. Go back to the oh right, okay. Let me grab the questions again. All right. Okay. So this is going to be this. All right, look at the answers here. So this means we want the set of all real values of x such that x is not -2. I want all real numbers except -2. So it usually helps to do the graph first. So we want all real numbers at first, so we color in this whole number line purple. But because we exclude the -2, we hop over the -2. We put an open circle there, an open circle, a hole there. It's literally called a hole sometimes. All right, and then from here we can get the interval form. We have a left wing and a right wing, so no middle wing. All right, what's the left wing? We want all the numbers less than -2. The left arrowhead you can kind of think of as -infinity. All right, and you got to follow the number line left to right. Parenthesis, it's always a parenthesis next to -infinity or infinity. Parenthesis, -infinity, comma. We go up towards the -2, but we don't touch it. We don't quite reach it. We still exclude the -2. So we have open parenthesis. We hop over the -2. If you hop over one or more numbers, you put this union symbol here, right? We have here a union of two connected intervals. One connected interval here, one connected interval here. Union, we hop over the -2, and then we want all real numbers greater than -2. Parenthesis, -2. Again, we exclude the -2 itself, comma, infinity, which you can kind of relate to the right arrowhead there. All right. Any questions about that? 0.1 number 6. Any questions about that?
I just wanted to clarify. So the slash means to like omit the 2, right?
The -2, right. It means it's set difference. So it means we want the set of all real numbers excluding the -2 and only the -2. That's called set difference form. Sometimes it's written with a minus sign, actually. That might be clearer. Yeah.
Yeah, because the way that it was written was confusing, but it makes
right. But actually, if you come to think of it, right? I mean, look at the answers. Whoops. Okay, because here's the deal. These guys is the same as this or this or this. Actually, this is the most compact. Of the 4 forms, these 4 expressions represent the same set, okay? You could argue that this is actually the most efficient. The set of all real numbers excluding the -2. Okay. In your Algebra 1 class, you might have just said, well, x cannot be -2, but that's an inequality. It's not a set of numbers. To write down the set of numbers, you technically need the subbuilder form if you're going to use this expression here. So you need the drapes on it. The set of all x in the reals such that x is not -2. Still, a lot of people view this as more compact up here. Actually, on an exam, I would tend to use the interval form because that forces people to graph.
Right.
All right.
Okay, thank you.
All right, you're welcome. Yeah. All right. Anything else? Anything else public for now? And then I'll switch to a private mode. But I would like to get these recordings, on the video where possible. Okay. So being generous for the students' benefit. Anything else public right now, or would you like me to go private? Anything else, public or private? All right. Any questions? Okay. You're welcome. Yes. Okay, any questions? Again, I may be available for some email over the weekend. Granted, I'm busy with stuff too, emails and maybe doing videos. But you're always welcome to shoot me an email, and hopefully I will check my email daily. Over the weekend, I try to check it a few times a day. Okay, anything else? Public or private? Public or private? Anything else? Oh, question here. Yes, I do intend to, unless there's a glitch. Will you be posting the recording of the session? Yes, excluding the copyrighted videos. I might actually post videos separately in their entirety on my YouTube account. Some of them. Some of them I have to edit, like Harold and Kumar. But yeah, for the most part, except for some of the copyrighted videos, I post recordings on my YouTube account. Later in the night or early the following morning. Yeah, the problem solving, right. And of course, now with the homework sessions, see, I leave it to the students because I'll start by recording, but if students want me to go private, I'll go private. So I cannot guarantee how much of the homework sessions will be public because if the students want to go private, I'll respect their wishes. Okay, which is why it's good to, if you have questions, you should show up at the Zoom session and you can opt for public or private. Okay. Basically, I want a combination of, a right balance between accessibility, but also respecting privacy. Oh, privacy is an issue. We're in the age of Facebook. Privacy is an issue. And don't be afraid to push that issue with your instructors. If you have an instructor who you feel is not respecting your privacy, then you can push that instructor. Bear in mind, a lot of the science professors do believe in webcams and video proctoring, so be aware of that. And I think that is legitimate. But it's also a reason why I don't like online testing. I'm not ready for that myself. Webcams, no thank you. Of me, fine, but okay, questions. Oh, thank you. Yeah, and I'm glad it works for people because it was a big risk going online, but I'm having a blast. I hope you are too. But I can't blame my colleagues who are having a hard time with it. It's tricky to come up with a good system. I'm lucky I'm good with my MacBook. Okay, questions? And already I can tell I'm enjoying having you already as students. Yeah, my last class was great too. Too bad we couldn't be on campus so I can see you and actually talk with you. But we'll make do. Oh yeah, I always try to be very prepared. I had to cut into office hours today though. I feel kind of bad about that. I should be better time managed than that. But yeah, lots of stuff going on. It takes time. All right. Take care, y'all. Any other questions? Okay, we still have about, what, 6 people in? Any other questions? All right. All right, have a good weekend. Yes. I'll stick around until it gets down to 1 participant, me, or it looks like people are walking their dogs. If I'm yelling out, who's out there? All right. So I'll wait another minute or so. If you want me to wait for you, if you're looking for something, just let me know. Chat. Wait up. Okay. Any last minute questions? Good night. Yes. Any questions before we sign off in about 20 seconds? Although if you want me to stick around, I'll stick around. Just let me know. All right. Speak now or forever hold your peace. Well, not forever. Maybe Tuesday. All right. Any questions? Any questions? Take care. Have a great weekend.